I've had several students who have asked me about questions number 6 and 7 on worksheet number 5. I inadvertently made these a little trickier than I had intended. What I will do is as I grade them, I will give full credit if you attempted to do it, but I'm also want to show you, so even though this is really a level of difficulty above what I would expect students to be able to do on an exam, you won't see anything nearly this difficult. It's still valuable to see, I think, and it illustrates how different genetics and environmental situations can have an impact on genotypes in a population. So I'm going to walk through it. If you want to follow along, great. Maybe you actually figured it out. If you did, pat yourself on the back. It's kind of a little bit next level here. So we've set up this situation where we have had a change in the genetics. So instead of a incomplete dominant system, we have complete dominance. So both homozygous dominant and heterozygotes show the red phenotype, and the homozygous recessive shows the white phenotype. And we have two pollinators, a pollinator that only visits white flowers, and then a pollinator that visits red flowers. But remember, that pollinator can't discriminate genotypes because it's just looking at red flowers. And so that's where it gets a little bit tricky. The white part of the population is easy. Every time a white flower mates with another white flower, they're going to make white offspring. And so if we're assuming they're going to roughly re-represent themselves in the population, we recover those 250 little a genotypes, homozygous recessive genotypes, from the matings of these white flowers. But when we look at the red ones, it gets a little complicated. We have three possible types of crosses that can occur when red flowers mate with red flowers. And if we're assuming all other things are equal, then the proportion of these crossings is going to be proportional to how many individuals there are of each of the genotypes in the population. And the way this is derived is very similar to Hardy-Weinberg. If you don't follow along, that's really okay. But to figure out how many homozygous dominant crosses there would be, we just need to figure out the proportion of homozygous dominant in the red part of the flower population. So 1/3 of all of the red flowers are homozygous dominant. So these matings would occur 1/3 times 1/3, or approximately 1/9 of all of the matings would be big A crossing with another big A. And we know, of course, all of the resulting offspring of those would also be big A. Okay? So 1/9 out of the 750 individuals that would be represented in the next generation would be big A from this cross. Okay? Now for the next one, we'll skip down and we'll do this one. This one's a little easier. Now, when these individuals mate with one another, there are two possible outcomes, right? Half of their offspring are going to be big A, and then the other half of their offspring are going to be big A. Now, to figure out how frequently these would get together, we again do the proportions, 1/3 times 2/3, but because it can go either way, you can have your parent, this can be the pollinator or the pollinatee. Is that a word? The flower that is pollinated. Vice versa, we times it by 2. So we would do 1/3 times 2/3, which is 2/9, right? And then we would times that by 2. So 4/9 of all of the matings would be like this. And if half of their offspring are going to result in each of those genotypes, then for each of those, we have 2/9 of all of the total offspring would fall into these two categories. Okay. Now, the last one. This is a standard heterozygous, very classic cross that you learn probably in genetics or even Bio 1, or maybe even high school biology, right? A Punnett square. And so of this offspring, 1/4 of them would be big A. Half of them would be big A. And then the other half, would be little a. And so all we need to do is figure out the overall proportion of matings that would be like this. And to do that, all we do is times the frequency, which is 2/3 of the population by itself. So 2/3 times 2/3 is 4/9. So 4/9 of the matings would be like this. And of those 4/9, half of them, or 2/9, would be like that, heterozygotes. And then 1/9 would be homozygous dominant. And then the other remaining 1/9 would be homozygous recessive. So now we have put proportions for all of our genotypes, resulting in all the possible types of crossings that can occur with red flowers. And now all we would have to do if we wanted to figure out the total counts would be to divide the total number of red genotypes by these numbers. So 750 divided by 9 is about 83, a little bit more. but we'd have about 83 individuals that would be the result of that. So every 1/9 is 83 individuals with a little bit of rounding error. And so we'd have 83 individuals there. We would have 83 individuals there. Here we would have 166, right? And then these would all be 166. We could combine like terms before we did it also if we wanted to put all the AAs and everything together. But so now that we have all of these numbers, I have all of the big A's represent 332. I think I did my math right. You can double check me if you want. But all of the big A's should be 332 or so. Again, with some rounding errors, actually probably a little bit more than that. Should be big A's. Of these big A, little A's, it's also right around there, 332. And then this is the interesting part. 1/9 of them, or 83 individuals, would actually be little a, and then would become part of this population. So every generation, we would lose a few of the little a's into this part of the population. And so over time, we would see this dynamic where we would continually lose a some, but not very many as time passes on. But we continue to lose some of the little a's that are in these heterozygotes, and then they would become part of this part of the population, which is separated because of the pollination. Okay, so we would need to add to get our final counts, and this is why it was a little bit more complicated. 83 plus 50 is 233, right? 333, something like that. And then we just add up here the big A's are 332. Again, probably with some rounding error, 333.3 is probably what they all should be, but 333, so something like that. So that would be our count for the next generation. And if we did this again, we'd have different dynamics and proportions, again, the second generation, now that everything is even. And we would lose a few little a's to this part of the population. And every generation that would go. So in the subsequent generation, we have our genotype frequencies, but the pattern is what I really wanted to see. Okay, so if you didn't get these numbers, that's fine. Like I say, this was an extra level of difficulty. Now that we've figured out that, we've got the same basic thing going on here. But there's this added little wrinkle in that there's no more pollinator for this white flower. So these 250 individuals would die out because they can't reproduce. Any individuals that were created from the crossings of heterozygotes here, right, that remaining 83 that came over here, they would die out. In every generation, we lose a few of those little a alleles, okay? Now, the key to this is if you went on generation after generation. So the numbers here, which I probably should have asked more for the pattern instead of just the numbers, but the numbers here are going to be the same as the one above, right? Roughly a third of the population after this of each would fall into here. But then these guys are going to all die out. So in reality, because they can't reproduce, they would die and we would have 0, okay? And so we've got this dynamic where we'd have all red flowers, but a few white flowers that are surviving but not reproducing, so they don't make offspring. But these guys can make a few offspring every generation. Now, this is the key to number 7, and this is what I wanted to follow up with question 8. Did we completely remove the white flower trait from the population? And the answer is no, because we still have some heterozygotes. And every generation, we're going to have a few more heterozygotes. And then the follow-up, would it be possible to completely remove this white trait from the population given the current genetics and pollinators? Now, as this trend continues, every generation we're going to lose a few of those little A alleles whenever they get paired together. But the key is as that little A allele becomes more and more rare in the population, the chance of pairing them together becomes smaller and smaller. So we are going to continually remove the little a allele, recessive detrimental allele, but the process of removal is going to slow down the farther it goes along. And so if you want to think about it this way, your cost of being a carrier for a even fatal trait is proportional to how common that trait is in the population. If it's a 1 in a million thing, then your cost of carrying that trait is almost 0, negligible. Because the only time you have a fitness impact from being a carrier is if your mate is also a carrier. And if it's a 1 in a million thing, then it's a very, very low risk. And so this is why detrimental alleles, especially if they are recessive, can stay in the population for a really, really long time. Because the rarer they get, the less exposed those carriers are to the natural selection processes that remove that allele from the population. So this would be a very, very long process. And in fact, in an infinite size population, it would never go to zero. It'd get vanishingly small. Now, in real life populations, it gets smaller and smaller and smaller. And because genetic drift also plays a role in addition to this natural selection impact, and we've got some mating bias here also that's emphasizing it. But any detrimental allele gets small enough until genetic drift, which may be small if it's a large population, but genetic drift plays a little bit of a role also, and it becomes fixed in the population. So even though it's a long process, eventually, inevitably, the detrimental allele would be removed, but it might take tens of thousands or hundreds of thousands of generations. Now, the last one, the follow-up, if the situations were reversed, if the hoverfly, which is the pollinator for the red flowers, had gone extinct, instead of, I think it was a moth that was pollinating the white flowers, we would immediately remove all of the big A alleles from the population. And within a single generation, red trait would be extinct and all of the flowers would be white. And so when it is a dominant allele that is detrimental, it can't hide. There's no such thing as a carrier when you're looking at the dominant allele. So it only takes one generation of complete selection to remove a dominant allele that is detrimental, but it might take tens of thousands or hundreds of thousands of generations to remove a recessive allele that is detrimental. Now, very commonly, I have students that confuse this idea of dominant and recessive in their head with beneficial and detrimental. Remember, when we say dominant versus recessive, we're not making any measurement of whether the dominant trait is good or bad or whether the recessive trait is good or bad. All we're saying is this is how the genetics work. Dominant traits can be beneficial. Dominant traits can be detrimental. But again, detrimental dominant traits tend to be very highly exposed to natural selection, and so we don't see very many of them in populations. But we see way more detrimental traits that are recessive because they can hide in the carrier condition and they get better and better at quote-unquote hiding as they become more rare.